Graph neural networks, GNNs, have shown remarkable success in various graph analytical tasks, but their effectiveness is often compromised in real-world scenarios due to distribution shifts, limiting their capacity for knowledge transfer across changing environments or domains. To address this issue, Unsupervised Graph Domain Adaptation, UGDA, has been introduced, aiming to facilitate knowledge transfer from a labeled source graph to an unlabeled target graph. Current UGDA efforts primarily focus on model-centric methods, such as employing domain invariant learning strategies and designing model architectures. However, a critical examination reveals the limitations inherent to these model-centric methods, while a data-centric method that modifies the source graph provably demonstrates considerable potential. This insight motivates the exploration of UGDA from a data-centric perspective. By revisiting the theoretical generalization bound for UGDA, two data-centric principles for UGDA are identified: the alignment principle and the rescaling principle. Guided by these principles, GraphAlign, a novel UGDA method, is proposed, which generates a small yet transferable graph. By exclusively training a GNN on this new graph with classic empirical risk minimization, GraphAlign attains exceptional performance on the target graph. Extensive experiments under various transfer scenarios demonstrate that GraphAlign outperforms the best baselines by an average of 2.16%. Training on the generated graph as small as 0.25% to 1% of the original training graph. Figure 1 illustrates the comparison between existing UGDA methods, which are all model-centric, and the proposed data-centric method GraphAlign. Graphs are ubiquitous data structures that model complex dependencies among entities, and GNNs have demonstrated considerable potential in various tasks related to graph data. However, they face notable challenges in real-world scenarios when distribution shift exists. Unsupervised Graph Domain Adaptation, UGDA, is a crucial task in node classification, where the goal is to train a graph neural network, GNN, model to accurately predict node labels in an unlabeled target graph, given a labeled source graph. Existing model-centric UGDA methods, however, are limited by their inability to address the distribution shift issue, which arises when the source and target graphs exhibit different distributions. To overcome this limitation, the authors propose two data-centric principles: the alignment principle and the rescaling principle. The alignment principle ensures that the source and target graphs are aligned in terms of their graph structures and node features, thereby reducing the distribution shift. The rescaling principle, on the other hand, rescales the node features to have similar scales across the source and target graphs, further mitigating the distribution shift effect. Guided by these principles, the authors develop a novel UGDA method, GraphAlign, which generates a small yet transferable graph for GNN training. GraphAlign achieves this by selecting a subset of nodes from the source graph that are most similar to the target graph, and then rescaling their features to match the target graph's distribution. This data-centric approach enables GraphAlign to outperform baseline methods in experiments, demonstrating its effectiveness in addressing the distribution shift issue in GNNs. By focusing on the data rather than the model, GraphAlign provides a more effective solution for UGDA tasks, offering a promising direction for future research in this field. The Contextual Stochastic Block Model, CSBM, is a generative model that integrates the Stochastic Block Model, SBM, with node features for random graph generation. In the context of Unsupervised Graph Domain Adaptation, UGDA, two distinct CSBMs can be used to model the source and target graphs, facilitating the examination of the domain shift. A motivating example demonstrates the inherent limitation in current model-centric UGDA methods that only focus on sophisticated graph neural network, GNN, model design. This example shows that existing UGDA model-centric methods would fail even for a simple case, where the classification error in the target domain is always larger than a strictly positive constant, regardless of the parameters of the GNN. In contrast, a data-centric approach is proposed, which modifies the source graph to construct a new graph that has the same distribution as the target graph. This approach is shown to be beneficial, as it can mitigate the inherent difference of the data distribution between the source and target domains. The GNN model trained on the modified graph can be seamlessly applied to the target graph, resulting in a reduction in the error in the target domain. Two principles are presented as guidelines for modifying source data in UGDA. A generalization bound is derived, which lays the theoretical foundation for these principles. The generalization error is defined as the classification error in the target domain, and the bound is derived based on the Lipschitz constant of the GNN model, the pseudo-dimension of the hypothesis set, and the alignment term between the source and target domains. The generalization bound is given by epsilon t, g, f, is less than or equal to epsilon s caret, g, f, plus eta plus 2L GNNW1, p, gs, p, gt, plus square root, 4d per nanosiemens, log, ens, d, plus 1 per nanosiemens, log 1, delta, where epsilon s caret, g, f, is the empirical classification error in the source domain, eta is the minimum error over all possible GNN models, and LGNN is the Lipschitz constant of the GNN model. The alignment term between the source and target domains is given by 2L GNNW1, p, gs, p, gt, which measures the difference between the source and target domains. The rescaling term is given by square root 4d per nanosiemens, log, ens, d, plus 1 per nanosiemens, log 1, delta, which depends on the pseudo-dimension of the hypothesis set and the number of samples in the source domain. The generalization bound provides a theoretical foundation for the data-centric principles in UGDA, which aim to modify the source data to reduce the difference between the source and target domains. GraphAlign is a novel unsupervised graph domain adaptation (UGDA) approach that adheres to the alignment and rescaling principles derived from the generalization bound analysis. It aims to generate a new graph that aligns well with the target graph, retains sufficient information from the source graph, and is significantly smaller in scale. The alignment principle suggests that aligning the distribution of the generated graph with that of the target graph can enhance generalization. To achieve this, GraphAlign optimizes the generated graph to minimize the Wasserstein distance between its distribution and the target graph's distribution. However, computing and minimizing the Wasserstein distance for graph data is computationally expensive and challenging, especially in non-Euclidean spaces. The authors present their solutions to these challenges, including how they relax the optimization problem and model the generated graph. They also provide a complexity analysis of their method. This research paper introduces a novel approach to address the problem of domain adaptation in graph neural networks, GNNs. The primary objective is to generate a new graph that aligns with the target graph and retains sufficient information from the source graph. To achieve this, the authors propose an optimization problem, which involves minimizing three main objectives: alignment, mimicry, and property preservation. The alignment objective aims to minimize the MMD distance between the generated and target graphs, ensuring they share similar distributions. For the mimicry objective, the authors focus on matching the gradients of the GNN parameters for the generated and source graphs. Lastly, the property preservation objective encourages the generated graph to exhibit real-world network properties, such as feature smoothness and sparsity. To solve this optimization problem, the decision variables are effectively reduced to the node features and the function that transforms these features into a graph structure. The authors also propose an initialization strategy for the generated graph's node features, which involves selecting nodes from the source graph based on their transferability. This selection is guided by the spectral distance between the generated and target graphs, as suggested by Theorem 2. This approach not only improves practical performance but also accelerates the optimization process. The proposed method leverages a surrogate GNN model to represent the mapping process, utilizing the GIN model due to its discriminative power akin to the Weisfeiler-Lehmann test. The generated graph structure is modeled as a function of the node features, using a multi-layer neural network. The optimization process can be handled using the Gumbel-Max reparameterization technique to deal with the non-differentiability of Bernoulli sampling. Overall, this paper presents a new perspective on domain adaptation in GNNs, focusing on generating a new graph that aligns with the target graph while retaining essential information from the source graph. The proposed approach has the potential to significantly enhance the performance of GNNs in various real-world applications. The complexity analysis of GraphAlign reveals that its time complexity is primarily determined by the optimization process of the generated graph G, which has a time complexity of O, R squared dn squared, where R is the reduction rate, D is the dimension of representations, and N is the number of nodes in G. The time complexity of the graph neural network, GNN, forward pass is O, D squared N, and the computation of L_alignment and L_mimic losses are O, RDN squared, and O, D squared N plus RD squared N, respectively. Overall, the time complexity of GraphAlign is O, R squared D plus RD plus R squared, N squared plus 1 plus R, D squared N. In the experimental setup, GraphAlign is evaluated under various transfer scenarios, including node classification in citation networks, airline activity data, and blogger friendship networks. The performance of GraphAlign is compared to baselines, including vanilla empirical risk minimization, non-graph domain adaptation methods, and unified graph domain adaptation, UGDA, methods. The implementation details of GraphAlign involve training a graph convolutional network, GCN, on the generated graph G, with and testing the GCN on the target graph. The hyperparameters used in the experiments include a reduction rate of 0.25% for ArXiv and 1% for the remaining datasets, and the values of alpha 1 and alpha 2 are set to 1 and 30, respectively. The experimental results show that GraphAlign surpasses all baselines and achieves an average improvement of plus 2.16% over the best baseline. The superior performance of GraphAlign is attained with the generated small graphs. The results are presented in Table 1 and Table 2, which show the performance of GraphAlign and the baselines across various settings. The reported numbers are the mean and standard deviation over 10 trials. Evaluations of various methods on graph domain adaptation tasks reveal the superior performance of GraphAlign, a proposed data-centric approach, in achieving higher micro-F1 scores across different transfer settings on citation networks, airport networks, and social networks. As shown in Tables 1 and 2, GraphAlign outperforms other methods, including empirical risk minimization, with various graph neural network, GNN, architectures, domain adversarial neural networks, DAN, conditional domain adversarial networks, CDAN, and others. This underscores the importance of adopting a data-centric approach over a model-centric approach in unsupervised graph domain adaptation, UGDA. The performance of GraphAlign highlights the need for a carefully tailored UGDA strategy to address domain discrepancy on graphs. Ablation studies demonstrate the effectiveness of GraphAlign's components, with removal of any loss function, alignment, lprop, or lmimic, or use of random initialization instead of the proposed initialization strategy, significantly decreasing performance. This emphasizes the critical importance of each component in enhancing GraphAlign's performance, specifically the alignment principle, gradient matching strategy, and preservation of graph properties when generating the new graph. The comparison of GraphAlign with other UGDA methods and ablation studies highlight the effectiveness of GraphAlign's data-centric approach in addressing domain discrepancy on graphs. This work demonstrates the critical need for a carefully designed UGDA strategy to improve graph transferability, with significant implications for developing effective UGDA methods in real-world applications. The authors delve into graph domain adaptation, GDA, through a data-centric approach, focusing on modifying the source graph to enhance its transferability to the target graph. They contend that existing methods, which concentrate on minimizing domain discrepancy metrics or employing adversarial training techniques, are limited as they view unsupervised graph domain adaptation, UGDA, from a model-centric perspective. In contrast, the authors propose a novel data-centric UGDA method, GraphAlign, which generates a small yet transferable graph from the original training graph. This modified graph is then used to train a graph neural network, GNN, using empirical risk minimization, The results in Table 4 demonstrate that GraphAlign achieves competitive performance with state-of-the-art methods, surpassing the most competitive baseline in several cases. A runtime and memory comparison of GraphAlign with other methods in Table 5 reveals that GraphAlign is more efficient. The authors discuss the limitations of existing UGDA methods, including their reliance on accurate estimation of target labels and limited modifications to the source graph. They emphasize the significance of their data-centric approach, which allows for modifications to graph structure, node features, and node labels. The authors also note that their method is purely data-centric, enabling the modified graph to be directly utilized for training a GNN by ERM. They connect their work to the concept of data-centric AI, which emphasizes the potential of data modification over model design. They discuss related research in graph data modification, graph condensation, and sparsification, but highlight the limitations of these methods in addressing UGDA. Overall, the authors conclude that their data-centric approach to UGDA has the potential to address the limitations of model-centric methods and achieve improved transferability to the target graph. This research paper presents a comprehensive list of 63 research papers on various topics, showcasing the breadth and depth of the field. The paper aims to provide an overview of the significant contributions made by researchers in different areas, highlighting novel ideas, methodologies, and findings. The list includes papers that explore cutting-edge technologies, theoretical frameworks, and empirical studies. These works cover a wide range of subjects, from advanced computational models to experimental investigations, all contributing to the advancement of knowledge in their respective fields. One notable aspect of this compilation is its emphasis on interdisciplinary approaches, demonstrating how researchers are drawing upon insights from multiple disciplines to tackle complex problems. This cross-pollination of ideas not only fosters innovation but also underscores the interconnectedness of different fields of study. A significant portion of the papers focus on addressing real-world challenges, such as environmental sustainability, healthcare, and social equity. These studies employ rigorous methodologies, including quantitative and qualitative analyses, to develop practical solutions that can be applied in various contexts. The compilation also highlights the importance of collaboration and international cooperation in research. Many of the papers are co-authored by researchers from different institutions and countries, reflecting the global nature of scientific inquiry and the value of diverse perspectives in advancing knowledge. In conclusion, this research paper provides a valuable resource for scholars and practitioners interested in staying abreast of the latest developments in various fields. By synthesizing information from a broad spectrum of research papers, it offers insights into emerging trends, methodologies, and areas of inquiry that are shaping the future of research. The appendix section of the paper provides a comprehensive overview of the notations used throughout the research, including graph-related notations such as adjacency matrices, node feature matrices, and node label matrices for the source graph, target graph, and generated graph. It also defines key terms like input space, representation space, label space, feature extractor, classifier, normal distribution, and probability matrix. The framework section details the pseudocode for the GraphAlign algorithm, which starts with initializing the generated graph. This process involves creating a specified number of plane nodes, calculating an adjacency matrix, and assigning labels to the nodes based on the distribution of node labels in the source graph. The algorithm then iteratively selects nodes from the source graph and the target graph, computes the spectral distance between their eigengraphs, and chooses the node set with the minimal spectral distance. The node features of the selected nodes are then assigned as the initial values for the generated graph. The initialization algorithm, denoted as algorithm 1, takes as input the source domain graph, target domain graph, reduction rate, and a threshold hyperparameter. It outputs the initialization for the node features and node labels of the generated graph. This algorithm involves multiple steps, including creating plane nodes, calculating an adjacency matrix using a ReLU and sigmoid function, and assigning labels to the nodes. It also involves iterating over a range of values, sampling eigengraphs from the source graph and target graph, computing the spectral distance, and choosing the node set with the minimal spectral distance. The GraphAlign algorithm is introduced to tackle graph domain adaptation by modifying data. It takes a source domain graph, target domain graph, and the number of iterations as input, and outputs a trained graph neural network, GNN, model. The algorithm consists of 3 stages: pre-training a surrogate GNN model, training the model on the modified graph, and updating node features and graph structure based on 3 losses: L-mimic, L-alignment, and L-prop. To evaluate GraphAlign, the authors compare it with various baselines, categorized as either model-centric or data-centric methods for unsupervised graph domain adaptation. These baselines include URM, MMD, CMD, DAN, CDAN, ADAGCN, UDAGCN, Mixup, EERM, SSReg, MFRreg, and STRURW. Experiments are conducted on 9 datasets: DBLPV7, Citation V1, ACM V9, DBLP small, ACM small, Corward, Caradegree, ArXiv degree, and ArXiv time. The dataset statistics are provided, including the number of nodes, edges, features, and classes. Implementation details are also provided, including hyperparameters and the running environment. The model is implemented using PyTorch, CUDA, NetworkX, Torch Geometric, Sklearn, NumPy, and Python, and experiments are conducted on a Linux system with an Intel Xeon Gold 5118 and a GeForce GTX Tesla P4. The maximum mean discrepancy (MMD) distance is estimated to measure the distribution discrepancy between the source and target graphs. The MMD distance is calculated using the Gaussian kernel and node representation matrices from the surrogate model. To enhance estimation efficiency, an equivalent number of nodes are sampled from the target graph. In this section, we delve deeper into the experimental results to further demonstrate the efficacy of the proposed GraphAlign method. We explore the impact of initialization on both the performance and convergence of the algorithm, comparing our proposed initialization method with several baseline methods including random, k-means, herding, k-center, and MMD. The results in Table 8 show that our proposed initialization method outperforms the baseline methods in most cases, achieving higher micro-F1 scores. We also analyze the impact of initialization on the loss convergence of the algorithm. Figure 5 illustrates a comparison between GraphAlign and a variant where the initialization is replaced with a random one. The results show that utilizing the GraphAlign initialization significantly enhances the optimization process, resulting in improved convergence characterized by a reduced loss. Furthermore, we investigate the impact of GraphAlign on the generalization bound for unsupervised graph domain adaptation, UGDA. Specifically, we examine the effect of GraphAlign on the value of eta, a critical parameter in the generalization bound. Table 9 compares the value of eta using the original source graph GS and the generated graph G, obtained through the proposed method. The results show that the proposed method effectively reduces the value of eta, highlighting its superiority in modifying data to address UGDA. Finally, we evaluate the transferability of GraphAlign across graphs with different homophily. We investigate the performance of the proposed method and baseline methods across different graphs with varying levels of homophily. The results demonstrate the effectiveness of GraphAlign in adapting to different graphs with varying homophily. The equations and algorithms presented in this section are critical to understanding the proposed method and its evaluation. Specifically, equation 1 defines the generalization bound for UGDA, which is impacted by the value of eta. The proposed initialization method is also presented in algorithm 1, which utilizes spectral distance delta spectral to initialize the nodes in the graph. The tables and figures presented in this section provide a clear and concise summary of the experimental results. Table 8 presents the micro-F1 scores of different initialization methods, while Table 9 compares the value of eta using the original source graph GS and the generated graph G. Figure 5 illustrates the loss curve between the initialization of GraphAlign and random initialization on the D-right pointing arrow task. Overall, this section provides a comprehensive evaluation of the proposed GraphAlign method, demonstrating its effectiveness in addressing UGDA and its transferability across graphs with different homophily. The results highlight the importance of the proposed initialization method and its impact on the performance and convergence of the algorithm. The authors evaluate the performance of GraphAlign on datasets with varying levels of homophily, a measure of node similarity in graphs. To simulate different homophily ratios, they generate target graphs using the preferential attachment method, while keeping the source graph fixed with a homophily ratio of 1.0. The results in Table 10 demonstrate that GraphAlign consistently outperforms existing methods, including MMD, DAN, and UDA-GCN, especially when encountering significant domain shift. Visualizing the representation distributions generated by GraphAlign and UDA-GCN using TSNE, a dimensionality reduction technique, reveals that GraphAlign produces more concentrated clusters of nodes in the same class, effectively reducing domain-irrelevant noise and differentiating between distributions of different classes. Figure 6. The authors provide theoretical proofs for the limitations of existing unsupervised graph domain adaptation (UGDA) methods and the generalization bound for UGDA. They demonstrate that most previous domain adaptation methods, which focus on learning domain invariant representations, are limited by the assumption that the distribution of the learned embedding is the same for the source and target graphs. However, this assumption is not always valid, especially when the source and target graphs have different structures. The authors also prove the generalization bound of UGDA, showing that the performance of a UGDA method depends on the similarity between the source and target graphs. Furthermore, they establish a theoretical connection between the property of the newly generated graph and the UGDA problem, indicating that the newly generated graph can be used to improve the performance of UGDA methods. These results demonstrate the effectiveness of GraphAlign in handling domain shift and its ability to reduce domain-irrelevant noise. The theoretical results provide a deeper understanding of the limitations and challenges of UGDA, highlighting the importance of considering the structure of the source and target graphs when designing UGDA methods. Graph neural networks, GNNs, have been shown to excel in various tasks, but their performance degrades significantly when faced with unseen data from different domains. This limitation stems from the inherent inability of traditional GNNs to generalize well across disparate domain distributions. To address this challenge, researchers have proposed a novel data-centric approach that modifies the source domain's graph structure to match the target domain's distribution, thereby enhancing the model's generalizability. The concept of domain adaptation is crucial in understanding the limitations of GNNs. Traditional GNNs tend to perform well on seen data but poorly on unseen data due to differences in domain distributions. To overcome this, the proposed approach involves constructing a new graph, G, from the source domain graph, G_S, such that the node representation distributions in both the source and target domains are similar. This is achieved using a single-layer GNN with a message-passing mechanism for aggregation, assuming a shared feature extractor, F, between the source and target domains. Mathematically, the approach involves modifying the graph structure to minimize the difference between the observed and expected node representations. The authors provide equations and algorithms to demonstrate how this can be achieved, including the use of Hoeffding's inequality to bound the probability of the difference between the observed and expected node representations. The classification error in the target domain can be minimized using this method, as shown through a detailed proof. The proposed data-centric approach has significant implications for improving the generalizability of GNNs in unseen data. By modifying the source domain's graph structure to match the target domain's distribution, the model's performance can be substantially enhanced. This research highlights the potential for this approach to address one of the major limitations of GNNs, paving the way for further improvements in the field. Addressing graph domain adaptation through data modification is explored by the authors. They begin by analyzing the optimal classifier in the source domain, which is given by setting x equals delta 4, resulting in a classification error of epsilon t is less than or equal to 1 express n delta caret 2 30 in the target domain. This error approaches 0 as delta decreases. The distance function loss serves as an upper bound to optimize and reduce the error. The authors then present Theorem 1, which provides an upper bound for the target domain error epsilon t, g, f, in terms of the source domain error epsilon s, g, f. the alignment term, and the rescaling term. Specifically, with a probability of at least 1 delta, epsilon t, g, f, is less than or equal to s, g, f, plus eta plus 2 L GNNW1, p, gs, p, gt, plus square root, 4d per nanosiemens log, e caret ns, d, plus 1 per nanosiemens log, 1, delta. Here, s, g, f, is the empirical classification error in the source domain. Eta is the optimal combined error. LGNN is the Lipschitz constant of the GNN model. W1, p, gs, p, gt, is the Wasserstein distance between the graph distributions of the source and target domains, and d is the pseudo-dimension of the hypothesis set. The proof of Theorem 1 involves bounding the target domain error in terms of the optimal combined error, and then relating the errors in the source and target domains using the Lipschitz constant. The bound is then linked with the empirical risk and labeled sample size, and finally derived using the Cauchy-Schwarz inequality. This novel result provides a fundamental understanding of graph domain adaptation and its relationship with data modification. The authors present Theorem 2, which establishes a bound on the transferability of a graph neural network, GNN, graph encoder f in terms of the spectral distance between the newly generated graph G and the target graph GT. Specifically, the theorem states that the difference between the representations of G and GT is upperbounded by the sum of two terms. The first term is proportional to the spectral distance between G and GT, and the second term is a constant. The proof of Theorem 2 involves analyzing a K layer graph convolutional network, GCN, with a one-hop polynomial filter lambda, L, where L is the graph Laplacian. Focusing on the central node's representation, acquired through a K layer GCN utilizing a one-hop polynomial filter, the authors denote the representations of nodes I for all I equals 1. And in the final layer of the GCN as Z underscore I caret K. They demonstrate that the difference between Z underscore I caret K and Z underscore I caret K is upperbounded by a function of the spectral distance between G and GT. By recursively applying the Lipschitz continuity of the activation function sigma, the authors derive an upper bound for the hidden representation difference between G underscore I and GT underscore J, which is proportional to the L th power of the spectral distance between G underscore I and GT underscore J, where L is the number of layers. Finally, they obtain an upper bound for the center node representation difference, which is a function of the spectral distance between G and GT, and the difference in features between any two nodes. The theorem provides a guarantee on the transferability of the GNN graph encoder f in terms of the spectral distance between the input graphs. Theoretical connections between Wasserstein distance and maximum mean discrepancy (MMD) distance are established, demonstrating that MMD distance can provide a bounded interval for the Wasserstein distance. Specifically, Theorem 3 states that, given two graphs G1 and G2, the MMD distance between their probability measures p, G1, and p, G2, is bounded by the Wasserstein distance, which is further bounded by the square root of the sum of the squared MMD distance and a constant tau. To prove Theorem 3, we first define the MMD distance as the supremum of the integral of a function f with respect to the difference between the two probability measures, where f is a function in a reproducing kernel Hilbert space, RKHS, H with a norm less than or equal to 1. The Wasserstein distance is defined as the infimum of the integral of a cost function c, x, with respect to a joint probability measure gamma, where gamma is a probability measure on the product space x times x. By assuming the cost function in the Wasserstein distance to be c, x equals phi x h, where phi is a mapping from X to H. We establish a link between the Wasserstein distance and the MMD distance. The key result is that the MMD distance is bounded by the Wasserstein distance, which is further bounded by the square root of the sum of the squared MMD distance and a constant tau. The constant tau is defined as the sum of the norms of the mean values of the two probability measures in the RKHSH. This connection between Wasserstein distance and MMD distance has significant implications for graph domain adaptation, as it provides a way to bound the Wasserstein distance between two graphs using the MMD distance. This result can be used to develop new algorithms for graph domain adaptation that are based on the MMD distance. The established connection builds upon previous work, including the results in 1948, 76, and has important implications for graph domain adaptation.